Good afternoon, Professor.
Good afternoon. Whoa, that was like, wow. Okay. That first of all, not that it's a race at all, but I think that, wow, I think Daniel and Stephanie just totally broke through the line at the same time. I'm so touched. And that was voice involved. I mean, okay, I'm not going to yes, I am. But good afternoon, both of you. Good afternoon, Stephanie. I think that was Stephanie, right? Or am I crazy?
Yeah.
Okay. Wow. Well done. You just made you and Daniel and everybody, and even people that are not thinking that I'm talking about them, and 10,000 other people made my day. 11,000 other people. Okay. So wait, no, but thank you for saying good afternoon. Okay. I'm still, and also that was all before 12:15. Can I point out that Daniel and Stephanie and anybody who just said good afternoon was actually also before 12:15. So, oh my God. Amazing. Wait, there's someone else. Okay, I will say good afternoon officially in a second. And this whole good afternoon thing is becoming like a thing. Also, have I ever mentioned that, obviously one of the reasons that I'm a physics professor is like every other physics professor, I secretly fantasize about being the person that someday is going to invent a time machine. But what's really sad about my secret fantasy is that if I invented a time machine, like it wouldn't be to go see the dinosaurs or go predict the stock market or something. I mean, I would make a time machine so that I could go like 6.5 minutes into the future and thereby actually not be late for whatever my next appointment is. That's about the most sophisticated use I could. Anyway, all right. Good afternoon, Daniel. Good afternoon, Mariam. Good afternoon, Stephanie. Good afternoon, Nikaya. Hi, Ashley. Good afternoon, Alyssa. Good afternoon, Jenna. Good afternoon, Jerry. Good afternoon, Luna. Good afternoon, Darina. Good afternoon, Yorgelis. Good. Okay, I feel that Ashley has a point when she says that the rich already have one, or it's already invented and it went horribly wrong. That is very funny. I don't even get it, and it's funny. Yes. I think, in fact, Steve Jobs, no, not Steve Jobs, an early computer dude, like super early, like what was his name? Someone like between Alan Turing and Steve Jobs is quoted as having said, "The future is already here. It's just not uniformly distributed," which somehow seems to relate to Ashley's quote. Okay, anyway, all right. We have to do physics, blah, 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 blah. Hello, everybody. Oh, and special hello to Stephanie and Ashley and Amarani for, in fact, showing something other than a black box, which I totally appreciate. And don't get me wrong, some of my best friends are boxes. But okay. And also, I don't think I said hello. Oh, and more people are coming. Hold on. Okay. And hello to 11,000 other people who make me very happy in a very different and unexpected way. Hello, Camilla. Oh, no, I shouldn't. I jumped the gun on that. All right. We are going to do more physics. We are going to continue with math. Hello, Camilla. Good afternoon. Thank you for saying so. And did I miss anybody? Did I say hello, Alyssa? I think I did. Okay, anyway. Yes, hello. Awesome. Thank you. I appreciate it. And that's points. It's all about points and Mario coins. All right, we're going to continue with the math method stuff. Like what we're now finally, now we're in a different zone here. We're now, if everything is like that or something, and we've been sort of climbing, like trying to like extract the differential equation from the physics of a mass on a spring, or we've been trying to extract a differential equation from the general relationships underlying a harmonic oscillator, if that's what we've been trying to do. And I think we have finally done it. Like what we finally now have is a differential equation, a second order differential equation that just, good afternoon, direct chat person, sorry. Yes, good afternoon. Thank you. Good to see you. If we now have a second order differential equation that describes the physics of a harmonic oscillator. And if then what we're now doing, like we spent a long time sort of churning the math to figure out that differential equation and to figure out a solution to it. Like, and that's what's written in the middle of the page again. And I can't emphasize enough, again, what we have in the middle of the page is a differential equation, and then its solution. To many of us, it still might, the solution might not look like a solution. Like to many of us, it still might be unclear. Why is the differential equation like the question? And why is the solution the answer? Like to many of us, we're used to thinking of equations themselves as either things that pose questions, or equations are like things that you plug into and then solve problems with. How is it that I'm calling this equation, this z thing, this function? Why is that an answer unto itself? It's an answer because it tells us how to predict, say, position as a function of time, or it tells us how to predict some dependent variable measurement as a function of some independent variable measurement, such as time, right? And that's what we want to do as physicists. You name the time, we name the position. So that's what we finally have arrived at. We've arrived at a solution to the second order differential equation. But again, also just to review for a second or reflect before we go on. Number one, you might notice that now on the page here, I mean, I've written something vaguely familiar, like what's in the middle of the page basically should strike you as basically what I wrote yesterday, 2 days ago, and the week before, but some slight subtleties. In the middle of the page, what's right there? First of all, I've been writing it with X's, and now suddenly I'm writing it with Z's. That's not a typo, but also you're not crazy if like that throws you for a minute. Or if you notice, we've been writing it with X's, and I'm going to start sometimes now writing it with Z's instead. Why? Not just to confuse you or like to be annoying. I'm doing it because this whole, we're always walking a fine line between the math and the physics. The physics is like particular situations in space and time that we are trying to make, that we are taking specific measurements of and then trying to make specific numerical predictions about. The math is the general relationships that apply to any set of such physical circumstances. And the math is like the language and the universal truths that are behind, that don't care whether we're talking about a specific spring of a specific stiffness or even a specific pendulum of a specific length or whatever, right? So there's the physics and the math, and of course they're very related. Just changing something, okay. But what motivated all, and we have to keep going back and forth, like we're doing the math so that we can do more physics, but sometimes in order to do the physics, we need to do the math. Okay, what motivated all of this was a mass going back and forth on a spring. It was going back and forth along an x-axis, like x stood for position anywhere along some line that the mass was occupying as it traveled back and forth on some spring, right? So we were analyzing, we did Hooke's law and Newton's law and found out, oh, that we can describe this motion with this second order differential equation. And it was a second order differential equation for which the dependent variable was x meaning where is the freaking mass? And the independent variable was t, meaning what time, like how much time have we been watching the mass, right? So we had a differential equation that was exactly the one written in the middle of the page, except it had x's in it, because that's what we eventually found out, like, oh, the second derivative of position with respect to time seems to be directly proportional to position, i.e. Hooke's law. Oh, the thing is pulled harder in the farther away it's pulled harder toward equilibrium, the farther away from equilibrium it is at any given moment. Like that's Hooke's law. That's a physical statement that we believe and that we converted, we expressed as a mathematical statement, right? So we were looking at X, and our goal was, and I know hopefully to many of this is sort of, increasingly clear. I'm in theory just reviewing here for a minute, but Hooke's law showed us that the second derivative of X with respect to time was directly proportional to X itself. And then we churned and churned math, and we did conjectures and thought about scatter plots and took guesses, and eventually realized, oh, if that's the case, then we verified and said with confidence, oh, if we want to predict where the mass is at any given moment, it's going to be a cosine function of time. And there's going to be some constants in there, omega and x, blah, blah, blah. So we got this thing from d2x, from, again, I'm saying what it used to be written in terms of x's, right, on this sheet. We had d2x over dt squared equals negative omega squared x. And from that, we solved and we said, okay, that's very good information. That's great. That's very complete information. But if we want it in a form that allows predictions, if we want to get x as a function of t, it turns out we found out x equals x naught cosine omega t. Now what I'm saying is, if we really believe that math that we did that math in order to analyze a mass on a spring. But if we really believe the math, math is math. We may or may not have liked it, but if we believe the math we were doing, math is math. And the math didn't care or even know that we were thinking about a particular coil of metal or a particular hunk of mass, like sitting on a table, traversing the x-axis. The math didn't care about any of that math. The math was just looking at the relationship between variable measured quantities. So X could have been anything, is what I'm from here on saying. Whenever I put a Z in there now, I'm not trying to throw you off or be careless. I'm often now going to put Z in there because what I'm trying to say with Z, maybe I said this yesterday, I don't actually think I did. Sorry, I'm just going to make a mark here. When I say Z now, by Z, I mean any, what you might call generalized dependent variable. From now, in other words, whatever we said about X should be true regardless of what X stands for. If we were to look at a pendulum going back and forth, not along a straight axis called X, but back and forth along some arc of some circle, as I think you did in lab 2, right, where people have. If we look at a pendulum for which the most sort of natural or descriptive measurement to think about would be its angular position along, right, some arc, rather than its linear position X, we might most naturally measure theta when we're talking about a pendulum. If we come to a conclusion that the second derivative of theta with respect to time is directly proportional to theta in this manner of this differential equation, then all the math that we did with X the other day would work for theta. Like again, the math doesn't care what letter of the alphabet we're using. So anything we found out about how X works would work with theta, and that would mean that theta apparently would oscillate cosinusoidally in some manner that is constant in time. In other words, from here on in, whatever we learned about a mass on a spring is going to be true of any physical system in the world. Any measurement we ever make that is dependent on time, if we have some good reason to believe that that dependent variable can be described by that differential equation, if the second time derivative of any dependent variable measurement, if the second time derivative of any measurement you think of, if the second time derivative of it is directly proportional to it, like with a negative sign, then that means that that variable is oscillating harmonically with an angular frequency that is the square root of the constant of proportionality. In other words, it means that cosine thing and that omega thing, anything we've said for the last 2 days, applies to any variable you can measure or conceive of measuring, as long as that differential equation applies. If that differential equation is true, then the solution is true regardless of the dependent variable. So it could be theta, like as in a pendulum. It could be capital E to stand for electric field, which we'll get to in this class. Or it could be something completely unexpected, something that, in other words, you don't have to see a coil of metal necessarily to realize that some system is springy. Lots of systems are springy, even if they don't actually have a spring. To be springy means act like a spring. To act like a spring means to oscillate harmonically, which means to be described by this differential equation and to be predicted by this solution. And finally, so I'm saying now, whenever you see Z's, it means I'm reminding you that this relationship is true for any variable, any dependent variable you can depend on, you can imagine, as long as it's depending on time. Like I am assuming, and in this sense, we're still a physics class, our independent variable for this whole context is always time. But any variable that fits this will fit that solution. And now, last thing in English, I made a big point of this yesterday, so I'm not going to like write it down again right now. But what's in the center of the page is mathematically the definition of a harmonic oscillator. A harmonic oscillator is something that is described by that second order differential equation. And harmonic oscillators have that at least as one possible solution to them. You also notice I added a blue mark to the parentheses. We're going to get to that blue thing today in math methods. Like that makes it a little bit longer than what I mean, that's a detail that I'll add today, but everything else you recognize. That's the math of harmonic oscillation. I guess I should say that one more time clearly. Like everything in the center of the page here this is the math of simple harmonic oscillation. And let's remember also from yesterday or from Tuesday, oscillation means going back and forth in any general way. To oscillate is to undergo a cyclical or periodic, i.e. repetitive back and forth type of motion. And it could be literally back and forth in a line, or it could be back and forth like this, or it could be like the magnitude of some like a temperature going back and forth, like homework 3, anything that's oscillation. Harmonic oscillation, as we said yesterday, harmonic oscillation specifically means, and you may want to write this down again, even if it was written down yesterday, or if it's all fuzzy in your mind, the big conclusion of yesterday was for something to oscillate harmonically means that it's oscillating with a frequency that is constant, omega, 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 has an omega. Something that oscillates harmonically has a angular frequency and therefore a frequency and therefore a period that is constant and far deeper, far more important, not just constant, not any old constant, but a constant that is independent of amplitude. That was our big conclusion yesterday. That's an English point. I'm not writing it down because I want to force myself to move on, but I highly suggest you write it down again. In English, a harmonic oscillator is an oscillator whose frequency in time is constant and independent of amplitude in space. A harmonic oscillator will go back and forth at a rate that does not depend on how you set it up or how far you initially stretch it or how not far you stretch it. An oscillator oscillates at a rate in time that is only dependent on parameters, on the ingredients of the oscillator. Example, mass on a spring, the angular frequency is square root of k over m. There is no x naught in that equation, is what I'm saying. Omega depends on k, stiffness, and it depends on m, mass, but it does not depend on x naught, initial maximum position. Like it doesn't matter how you set that thing up. It just matters what thing you're setting up. Okay, so anyway, in the middle of the page, so what I'm saying from now on is anything that behaves that way behaves that way. Anything in life from now on that we call an oscillator, we're saying acts like a mass on a spring. If you could picture a mass on a spring and everything that it does, everything that we spent like a month and a half now analyzing, all the questions on homework 1, energy conservation, equilibrium spot, trade-off between speed and position, all that stuff, all this differential stuff, anything you now believe about a mass on a spring from here on in, I'm saying anything that we call springing means we're saying it acts like that in all respects. And to know that something acts like that in all respects, all you have to know is that it's described by this differential equation. And whatever the dependent variable is, could be angular position, could be electric field, could be gravitational field, could be temperature, pressure, whatever. Okay. Now I'm going to go on. Oh, so now what's the math? What's homework 2? What's the math methods sheet that we're now in the middle of? We're just now practicing, seeing how what the math is doing for us now that we have a solution. So we're sort of practicing different possible solutions to the differential equation and different versions of the differential equation. One last thing you'll notice, this blue bit that's in the parentheses, you've never seen it before. It's going to come up as we go over the math today. And then you see this thing down below with E. We've never said that yet. It's going to come up today. But the two things suggest one ultimate lesson. We have a differential equation that describes harmonic oscillation. We are looking for living all the wrong places, we're looking for a solution always, right? Which means we have a statement about derivatives, but we're looking for a statement about, oh, thank you, I appreciate that. Oh my God, don't get me started on all the songs about moons that I'd like to sing right now. Okay, that's how good my singing is. You're laughing. I'm so hurt. I am kind of, no, okay. I mean, sorry. But thank you for, that's points, by the way. It's totally points. I'm going to open up a portal, not only for people that are still paying attention, even as I drift into ADHD land, but, and no offense, some of my best friends live in lands, but I'm also going to give points for anybody who is willing to acknowledge my deep musical talent. Okay, wait. Oh, I understand that the thing at the bottom of the page, might not look like it makes any sense to some of you. Like, it does assume that you've tried homework 2, and that's what we're going to go over now. It's nothing I've said yet in class. Same thing with that blue mark in the middle of the parentheses. I haven't said anything about that yet in class, but here's what I'm suggesting that, oh, yeah, this is what I'm going to say. What I'm suggesting is we have a differential equation. The physics presented it to us. Again, it's not because this is a math class, and where it's not the alphabet of differential equations. It's just that Hooke's law, once you just like write it down and you substitute it into Newton's second law, you suddenly you're like, oh my God, we have a second derivative equaling something. So I have to like deal now. Like, the physics just forces us to deal with the math. We're looking for a solution, right? We're looking for a straight up, I mean, we have one, don't get me wrong, but we've been looking for one. But here's my point. We were looking for something that solves the differential equation, a relationship between dependent variable and independent variable. We found one. It was the cosine omega t thing. What I'm going to try to emphasize starting right this minute as I turn the page to homework 2, what I want to emphasize is what we have found indeed is a solution. Yes, we have found a solution to the differential equation, a super useful solution, one that we'll use for physics. But please understand, what we have found is a solution, not the solution. Or put another way, not the only. We have found something that works. It doesn't mean that it's the only thing that works. In fact, it's not the only thing that works. So what we're going to find out today when we go over the math is that when we say x equals x naught cosine omega t, right? That totally works, and that gives us a lot of information. No one ever said it was the only thing that works. It may be a very specific version of a whole set of things that work. That's what we're going to sort of find out. So that's why there's more written on the page than you've seen before, because now we're going to find out that there's more than one ways to skin a metaphorical cat, and they're all metaphorically gross. Okay, so let's, wait, actually, I'm going to switch. So what are we going over? We're back. We are going, I'm just going to switch the screens for a second and put up, just so that we know what we're talking about. Hello, what's going on? We are, sorry, pause for 1 second. I could have sworn I set this up in advance. Yeah, sure you did. Yeah, Rebecca. Oh, yeah, okay, so that's that. So what's the problem? Okay, yeah. All right. So I think the screen just shifted on your end, I hope. So what we're looking at, so I'm just, again, hopefully you have this in front of you, depending on who you are. If you are some of my newfound friends in the world whose attention I really appreciate, then you may not have this sheet. So I'm showing you what we went over yesterday. Yes, okay, so we were going over this Tuesday, I mean, right? And we got through question C. We said, so, well, basically, it gave us a proposed solution, a function, x equals a cosine 5t. And then we, having gotten used to this method from the first 2 questions and from last class, we took a derivative of x with respect to t, then we took another derivative of x with respect to t to see if indeed what we found at the end of the day was negative 3x, and we didn't. What we found at the end of the day was negative 25x. So we decided, and so I'm just reviewing quickly. So part C, the thing that's hopefully looking at you in the face right now on the screen, part C, we said the answer is no, it is not a solution. It is not. And why? And so the answer, why not? Because 25 does not equal 3. Like, literally, that is our reason. Our reason, I mean, we're saying that function is not a solution, does not satisfy, does not solve that differential equation. Again, in part C, it does not, because 25 doesn't equal 3, i.e. when you take 2 derivatives of that x, you get negative 25x. You don't get negative 3x. Now, the reason we did it, though, you might say, well, why do we waste our time on that? Because I'm trying to show you like that not everything is automatically a solution to a differential equation. And even if something sort of looks like it has the right format, even if it has a cosine in it, any cosine function like the one written in C is the solution to some differential equation. And in fact, some oscillator. But what we're really saying in English in part C, when we say that that function does not solve that differential equation, what we're really saying is that we have two different oscillators in mind. One of those is a description of one oscillator, a harmonic oscillator, and the other, like the differential equation, is describing a harmonic oscillator, and the solution is describing a different harmonic oscillator. In fact, let me be even more specific, and you might even want to write this if you're doing the homework or correcting your homework or getting more points on your homework. Like if I say 25 doesn't equal 3, I suppose that's a little bit glib, although it's certainly true. What I'm really saying in a way is the differential equation is describing, and I should almost add this to the homework, but the differential equation, look at it from, again, I'm talking about part C here, and I know we did it already, but now I am actually saying something new. It may be helpful to some people. If you look at the differential equation in part C, once you're getting used to all this, you realize that is describing a simple harmonic oscillator. It is. And specifically, it's describing a simple harmonic oscillator whose angular frequency, whose omega, whose number of radians that it's doing per second is square root of 3. Let me say that one more time. You might want to make a note of that. And if you get what I'm saying, then you're definitely with me. If you want to think for a minute, there's no shame, but you might want to think for a minute. I'm saying I look at that differential equation and I immediately know we've got a simple harmonic oscillator whose omega, whose angular frequency is the square root of 3. And I'm saying it for reasons that once you've done all this math are as simple as can be. I'm saying from here on in, whenever I see, this is sort of my point of whether that was an X or a Z or a Y. If I see that the second time derivative of some variable equals negative times a constant times that variable, then I know immediately two things. One, it's a harmonic oscillator, simple harmonic oscillator. And two, I know that it's oscillating with a frequency, an angular frequency, which is necessarily the square root of whatever that constant is. Honestly, that is why we always call that constant omega squared. That used to really confuse me, and I'm not joking. Like if you look, in other words, C is just a specific example of what's written in the middle of B, right? Okay, C is just a specific example of the general form that's written in B, which was also written on the first page a minute ago on the other screen, right? And whenever you see that omega squared, I want to emphasize to you, that makes it look like it's some kind of variable or some kind of fancy thing that used to always throw me, honestly, that it's squared there. Omega squared is just a number. Omega squared is just a constant. It is just a constant. In fact, in the case of a mass on a spring, it's another way of saying K over M, like literally K over M. It's just a number. But we could have called it beta. We could have called it C for constant. We actually could have just called it omega. But the reason we call it omega squared is Monday morning quarterback, is like the benefit of hindsight. Because what we're saying, we now know, having played around with all this and gotten all the pieces out on the table, we're now saying from now on, whatever that constant is in that differential equation, it turns out, like since the solution is always X equals A cosine omega T, like the omega in the cosine thing, the angular frequency is always the square root of whatever is there. So we call whatever's there omega squared. You see, it's all a little bit weird retrofitting. That's why it's very fair for you not to get what I'm saying, sort of like the first pass through, because we really are passing round and round and putting all these pieces down, and then the whole table is set. It's really fair if you don't get what I'm saying the first time, because in a way, there's no correct way to say it the first time. You kind of have to see it there and back. No joke. So what I'm really saying is, why is that thing always called omega squared? Just because we in advance are predicting or knowing that the square root of it is going to be the thing that we call omega as an angular frequency. So, for example, in part C, I just look at that thing in the middle of part C. I should mark it, but the thing in the middle of part C, d2x dt squared equals negative 3x. I look at that and I immediately know, aha, simple harmonic oscillator, like cosine function, where the angular frequency is square root of 3, like not 3, but square root of 3. 3, in effect, is, in other words, is omega squared. Omega squared is 3. So omega is square root of 3. Okay, but, right, like that, I just know that. We could prove it again, but that's what we've been spending 3 weeks proving. But the proposed solution says x equals a cosine 5t. So in the solution, omega is 5. In the differential equation, omega is square root of 3. So they are not the same thing. One oscillator is going 5 radians per second, And the other one's going square root of 3 radians per second. And again, what do I mean radians per second? I mean, by radian, I mean a sixth of a cycle. Like not exactly, but truly. Why sixth? Because 2 pi is basically 6. So, and 2 pi radians is 1 cycle. So 1 radian is 1 2-pith of a cycle, right? So one oscillator here in part C is going at an angle at a rate of 5 radians per second. That's in effect 2.5 cycles per second. Do you see what I'm saying? Right? I mean, I'm doing this in my head, but this is where you want to get with it. Like all this stuff, all the cosines and the radians and everything, they're all about cycle, portions of cycles. An angle is a portion of a circle, i.e. a portion of a cycle. A radian is a sixth of a cycle, or put another way, there's 2 pi radians to a cycle. So I know I'm yelling because I'm getting excited because this stuff makes sense once it makes sense. It doesn't make sense until it makes sense, at which time it makes so much sense that you're like, it doesn't even make sense that I ever thought this didn't make sense. Like, duh, it's obvious. It's not obvious. Everything is obvious once it's clear, and it's completely insane until it's clear. What I'm saying here is it, and I will move on before I have a heart attack, but I'll only have a heart attack because I love you and the material so much. It's all about the love. In part C, where it says, is X equal A cosine 5t? When I look at that, I immediately say to myself, aha, that's an oscillator whose amplitude is called A, like it's called A, and who's going back and forth, going back and forth, going back and forth at 5 radians per second. And I know, 5 radians. Oh, I thought 5 pi second. So 5 radians per second. I know that there's exactly 2 pi radians in a cycle, so a little bit more than 6. So that thing is doing a little bit less than, and I did say this wrong about 3 minutes ago. That thing is doing a little bit less than 1 cycle per second, a little bit less. It's got a standard frequency of a little bit less than a hertz, 1 hertz. 1 hertz, by definition, is 1 cycle per second. That oscillator written in the X equals format is an oscillator with a standard frequency of a little bit less than a hertz. The other one, the differential equation, is also an oscillator, but it's a different one. That one has an angular frequency of about square root of 3 radians per second. Square root of 3 is about 1.75, 1.73, 1.7 something. God, I should know that, but like 1.7, let's call it. So it's about 1.7 radians. So that means a little less than 2 radians. So about a third. So that thing is going about a third of a cycle per second, about a third of a hertz. So they're both harmonic oscillators. They both might be equivalent in every other respect, but one is faster than the other. They're not the same. So the first expression is not a solution to the second expression. So that was supposedly reviewed. That's what we did yesterday. Okay, so then D, and then D, I'm not even going to, D is just checking everything I just said. I mean, we implicitly, I'm not even, is that a hand? No, it's my hand because we just lost the board. Oh, that's weird. Sorry, why am I here? I'm going to leave. Sorry, that's really weird. Okay. D, we did it yesterday in order to do C. D is like a check on C. It's sort of going out of order. I mean, the answer to one is, to D1 is dx dt equals negative 5a sine 5 of t. And the answer to the next part, to D Roman numeral 2, is d2x dt squared equals negative 25a cosine 5t. I mean, I think we said that Tuesday. I hope that's clear. Okay, now E. All right, I'm going to go back to the other board. Well, no, okay. E also hopefully is a little bit straightforward to you now that we've said all this. I don't want to dwell on E. E again is sort of plug and chug. E is just trying to show you again what we mean whenever we, like, for a strict mass on a spring, it turns out that omega equals square root of k over m, right? Because the constant in a strict mass on a spring, if you look back here to like C, right? Instead of just thinking of 3 as some arbitrary number, realize that when you do Hooke's law and you plug it into F net equals ma, what you get is d2x over dt squared equals negative k over mx. Like the constant is k over m if you just write out a generalized mass on a spring. So so that's omega squared. Omega squared is K over M for a mass on a spring. Therefore, omega is square root of K over M. So hopefully that's sort of clear. In other words, omega is what we say in general will be true even if we have a pendulum on a string. So we don't have a K. We have other constants involved, or even electric field. No matter what the other parameters of the particular physical situation are, they will determine omega. Like you might know already from lab 2. You might know for a pendulum, it turns out that omega is not square root of K over M. There is no K in a pendulum. And in fact, M is irrelevant in a pendulum because all objects fall due to gravity at the same rate. And gravity is so in a pendulum, omega turns out to be square root of G over L, where lowercase g is the 9.8 number, right? Notice though, in a pendulum, it's just like a spring, the omega depends on parameters. It depends only on the ingredients comprising the oscillator, nothing else. So omega is true for all oscillators. The particular details of omega differ from one physical oscillator to the next. That's really what's sort of happening here in E. So again, I'm just going to say this out loud because I want to, I don't know why, but so dx dt, so question E, part 3, the answer to the first derivative. Again, I'm using trigonometric derivatives and chain rule. Oh, also, please do stop. I mean, I'm acting like this is all obvious. It's none of this is obvious. If you still need help, if you are pausing on the or bumping on the chain rule or anything, again, please put it in the chat or mention to me or something. I'm just assuming because I've said it a couple of times, then that means something. But if you didn't know what I was talking about the first time, I said there's no reason you would know what I was talking about the third time I repeated the same thing. So the answer to dx dt for E3, dx dt, again, I'm looking in the middle of the page, is negative a square root of K over M sine parentheses square root of K over M times T, right? In other words, the square root of Km comes out just from chain rule, just like the omega did. And cosine turns to negative sine because of trig derivatives. So you get negative a square root of K over M sine parentheses square root of K over M times T. And then the second derivatives, you just do the same thing again. So then you get negative a K over M, like, because now it's square root squared. So negative a K over M cosine parentheses square root of K over M times T. I'm saying that because I think that's clear at this point. I think, but now I'm going to go on to stuff now I'm going to start writing out things for good or for bad. I'm going to switch boards. So if you need to quickly jot this down or whatever, I'm going to look at F, which is given x equals a cosine omega t plus the number 3.5, find the two derivatives. Now, this is worth pausing. I'm going to do this out. Just note, it looks like the same garbage we've been doing. It looks like the same stuff we've been doing over and over. But just now I've just sneaked in an extra number into that parentheses, in the argument of the cosine. I just stuck in a number there. And that's sort of obnoxious, but that's totally the point of this next exercise, to see what happens when I stick in a number. And I do want to emphasize that is an arbitrary number. Don't get hung up on it. There's nothing special about the 3.5. I just want to emphasize that it is a number. I should also point out that that number, whatever that number is, I mean, it happens to be 3.5 here for literally no reason, just for it to be a number. But I hope it's clear that even though it's a number that had better be measured in, or maybe I'll even pause while I switch boards. I'm going to ask if anybody wants to put in the chat, what units necessarily is, even if you don't know, like, even if I just made it up, even if I'm just making up an arbitrary example, if anything about this example is coherent or meaningful or works, what units must that 3.5 be measured in for any of this to make sense? So I'm asking you if you want to put in the chat or whatever, for points, for Mario coins, for money, not for money. I don't have money. But for what the question again, and I'm just going to ask it and I'm going to switch boards. What units must that 3.5 be measured in for this to make any sense? Okay, meanwhile, I'm switching boards. Am I? Wait, okay, I'll ask this just to make sure. Okay, if I'll repeat that question in a minute, but could someone tell me in the chat right now what I feel like is, it says that I've started screen sharing, but is it sharing anything? Do you see anything on you? Because it's black, right? No. Okay, thank you. Okay, thank you. And you totally got points for those answers. Thank the three. Thank you, Camilla. Thank you, Stephanie. Thank you, Camilla. And I don't know why I have to, let me try again. Hold on. But now that you all just answered that, the sad thing is that just means you are listening. So that means someone's got to answer. So I'm going to repeat the question. Or just, can I get some acknowledgement from anybody? It doesn't have to be Stephanie or Camilla or any. Can anybody acknowledge if they heard? If they're, you don't have to answer, and you don't have to be embarrassed. But all right, I'll take it. Good enough. So Camilla just said crickets for that question. Well, as long as I know that you do hear the question, though. Like, your point is you don't know the answer. I mean, that's okay. That's fair. But let me see if I can get this board work. But I'll repeat to everybody. I would like everybody to think. There's a 3.5 sitting in that parentheses. I'm asking us to consider a function. And by the way, one hint is just, this is raw. Like, you don't have to know the answer to the whole problem in order to see this. I'm asking you to consider the function x equals a cosine omega t plus 3.5, like the number 3.5. Now, just even if you don't know what we're doing, even before you take derivatives of that function or anything, just if we're considering the function, and I do want to write it down, so I do want my board back. I don't know who I'm talking to. God, can you provide me with a board? Thank you. Yeah, no, we have a very close relationship. He'll give me a board in a second, but not money. And it might be she. I'm sorry. I think it's both. What the heck? A cosine omega t plus 3.5. The omega t plus the 3.5 are all in parentheses. I'm insisting that for that expression even to make sense at all, 3.5 must be in certain units. And I'm asking what units it must be. Now, I will give you a hint, or I'll give you a couple of hints. You know what units omega t have to be in, or at least I think you do. Or put another way, I think you know what units omega are in. And I think the reason that omega is in the units that it's in, I think the reason the omega is there is because omega, we had to put something next to the t to make those units work out so that we could even take a cosine of it in the first place. Whatever that argument was, or that logic was, it has to apply to the 3.5 as well. Let me put it another way. I cannot add kilograms to meters. I can multiply kilograms by meters, which is a very strange thing, but I cannot add kilograms to meters. I can only add kilograms to kilograms. And when I do, what I get is kilograms. And that's not a joke, right? And I can add meters to meters because that's just an accumulation of meters. And what I get is more meters. So whatever that 3.5 is has to be in the same units as the omega t so that we can add them together and still be in the same units, the units of which we take a cosine. I don't know if that's a hint or not, but I'll let that sink in while I ask. Again, can I have a board, please? Let's see. Okay, I heard a sound. Okay, that's a good sound. Oh, good, two of me. That's just what we need. Okay, that's a good sound. I'm still getting cricket. At least do me a favor. I'm accepting Camilla. Camilla's totally getting points for at least saying cricket. She's acknowledging the question, right? And by the way, this is what I always tell everybody to do on their homework. If you think you don't know the answer to a question, start by putting in your own words what the question is. What I would love to see right now in the chat is any kind of, even anybody writes in the chat the question, if you even just write in the chat, what are the units of 3.5? First of all, I'll feel better as a human being. Second of all, I'll think you're one step closer to actually getting an answer. And third of all, you get major points. And in fact, I am going to make a portal for that, for just like repeating the question in the chat. So if anybody, Camilla's already done, as far as I'm concerned, she's acknowledged the question. If you could just put in the chat or raise your voice and just say what the question is, so I don't feel like I'm talking to a black box, that would be real. Now I'm really getting scared because I'm still getting nothing, but here comes the board. Oh, wait, you guys can you put in the chat whether you can hear me or not? Have I lost everything? Have I lost credibility? Okay, whoa, okay, now it's coming. Whew, whew, okay. Smelling small. Okay. All right, cool. Thank you very much, Stephanie. Thank you very much, Mariam. Oh, and also Mariam made a joke before too. Sorry, I missed that. She totally got the point for that. Thank you, Amarani. Thank you, Stephanie. Okay, yes. So just, and everybody look in the chat. Right, okay. So all right. So that is my question. Now, part of the deal of me doing this is I'm promising I'm not gonna force you to get the answer, but I think when you see it, you should tell me whether it makes sense or not. Let me now got my board. Let me tell you what we're working on here. What we're doing is hello. Okay. One thing is I don't know why. I don't know why it's Roman numeral 3, not Roman. I don't know why. Okay, I'm going to say that for so yeah, I'm asking even before you get to the question what units 3.5 is, and okay, I'm going to assume there is some confusion here. I'm going to say it, but please tell me if this either does or does not make sense. I'm saying this 3.5, which is just a number that I'm sticking. This 3.5 must be measured in radians, folks. It must. First of all, this whole thing here must be measured in radians. You do want to, and again, please, whenever I say radian from here on in, I know there's a tendency if someone says radian to be like, oh, me, or to be like fog. Like I just always, whenever I had to deal with radians, I just like fogged it out and dealt with what I had to deal with and moved on. And I never grokked it. But I'm telling you, when I say radian, picture a sixth of a cycle. It's literally what it means. It's a sixth of a cycle. Or if you don't like six, picture portion of cycle. A radian is just a part of a cycle. Whenever we're thinking radians, we're thinking of cycles. All of these things are oscillators. They're cycling back and forth. Omega t has to be measured in radians because you can't take the cosine of anything other than something measured in radians. The omega came in the first place, like omega itself was measured in radians per second because we knew that time was measured in seconds. Okay, like that's how this all came about. Something is happening in time, something's going back and forth in time. We think that cosine might be the mathematical way to describe something going back and forth in time, but you can't take the cosine of a second. You could take the cosine of a radian. So we figured there had to be something next to the time, that constant measured in radians per seconds to cancel out the seconds and give us radians. That's where right? And that's all we knew about omega in the first place. Just some constant that described rate of cycling per time. We've learned more and more about it since then. But when we first stuck it in there, we were literally just sticking in there because the units demanded it. But let's not forget, the units demanded it because you've got to take the cosine of only something measured in radians. So similarly, if omega times t is measured in radians, then the only thing we could add or subtract from radians are other radians. That number 3.5, whatever it is, has to be measured in radians. And by the way, the reason I'm making a big point about the units is the units. And again, like anything else, when you're first dealing with them in science, like they're super annoying, or you just like do what you have to do and you move on with your life. But the fact of the matter is the measurement units are exactly what distinguish the physics from the math. The measurement units are what remind us that we're thinking about this like scientists, and it often gives us a major leg up over the math. Because I'm going to do something with that 3.5 number, like it's there for a reason. We're going to have to, it's there to signify something in the physical world. And my first hint as to what it is it's something about the cycle. Like it's got to be like it's some portion of the cycle. Maybe I'll even go so far as to say it's presumably some kind of head start or delay in cycle. Like 3.5 literally means 3.5 radians. which means about a half of a cycle for whatever it's worth. Can I just get anything in the chat all just to say, like, if you, and I'm not trying to yell or be angry, but do you get what, like, do you get the 3.5, whatever it is, even though I just threw it in there? Can anybody put in the chat that you understand that it's measured in radians? Or am I being like that guy? Or am I being someone? I'm so scared. Wait, now there's like major. Okay, that's good. Thank you. Oh, that was. Oh, wow. All right, I totally. Thank you. I totally appreciate it. That was fine. They got. That's fair. That's honest. That's cool. Yes, I can. All right, I'm going to explain it again. Yes, but thank you all for responding at all. And by the way, some of you responded in direct chat. That is totally kosher. Is totally kosher. And all of you get points for that. For those of us, I mean, seriously, whether it's direct or not. But yes, thank you for having the guts. I should put a portal for that. Thank you for having the guts to say, can you explain it again? Absolutely. We're about to look at a function, x equals a cosine omega t plus 3.5. Now, first of all, it's a given in this problem. So I want to remind you, it's just a function that I'm presenting to you. I'm not asking, like, I'm just stating this function. I'm thinking this function, I want to consider it. So in other words, there's no reason that I'm not saying that you should see that the meaning of the whole function right away, or what it means or what it signifies. Or I'm not saying there's any reason why I came up with a 3.5 yet. But I'm saying if I stuck that 3.5 in the parentheses and asked you to consider it, it has to have units of radians. All I'm really saying is the 3.5 has to have units of radians, because you can only take the cosine of something that is measured in radians. And just like omega t, therefore, itself had to be measured in radians, so I could take the cosine of it, then anything I'm adding to omega t to complete that parentheses has to also be measured in radians. Basically, this whole function is saying cosine of something measured in radians plus something else measured in radians, one big pile of radians. I'm taking the cosine of it. So I'm saying, just from the fact, I'm just saying the fact that the 3.5 is sitting in the parentheses, even if you don't know why I put it there or where it came from or exactly what it means, whatever it means, it must be some number of radians. That's what I'm saying, that the 3.5 has to signify some number of radians, which means it has to signify some portion of a cycle. Cool, thank you. And that's more points for closing a conversation, for real. Thank you. No, thank you. Really, this is called class. I totally appreciate it. Thank you. All right, but so now I'm gonna, okay, seriously. And for those of you who, anyway, some of you in the class should be thanking her for having the honesty to make me do that. And I'm going to stop pointing my finger now because it's mean. Okay. So now our job is to take the derivative of it, just because it's asking. It's just saying, like, can we take the derivative of this? Okay, I'll take the derivative. I'm going to use trigonometric derivatives. I'm going to use the chain rule. So I'm going to say, I'm going to change my color. Not of me, but of the pen. So I'm saying, oh, and I should pause it. Okay, that's the answer, first of all, to that question. That is the answer. Maybe I even skipped a step in the work. That is the answer. I guess what I want to make absolutely clear why I did that. Like, just to be absolutely clear, what I'm really saying is, notice with that 3.5, and we're not done. I'm just done with that exercise. And all it is right now is just an exercise to show just practice derivatives. But even though I stuck the 3.5 in the original function, when I take the derivative of it, the derivative of cosine is negative sine, just like before. And I have to do the chain rule because I'm doing a function of a function. Like, I'm not just taking the sine of t, I'm taking the sine of, I'm sorry, I'm not just taking the cosine of t, I'm taking the cosine of omega t plus 3.5. So I'm taking the cosine of an embedded function. The embedded function, call it y of t, right, is omega t plus 3.5. So the chain rule says I'm supposed to take the derivative of that and multiply by the whole outer function, right? Just like I did before. So that is what I'm doing here. But notice the derivative of, like, the derivative of omega t was just omega. The derivative of omega t plus 3.5 is still just omega, right? Because 3.5 is a number. It's a constant. It doesn't have any variable in it. In other words, what's the derivative of 3.5? It's 0. Right. So technically, you could say this omega that I just wrote here at the bottom of the page in blue. Technically, I'm saying the derivative of the derivative dy dt. That's very bad here. I'm saying technically, the derivative dy dt, you could say, is omega plus 0, right? Like there's no derivative of that 3.5 number. So what? So the 3.5 is there, like it's still getting carried along for the ride. It's still in the parentheses, but the omega comes out. Only the omega comes out. And so my derivative, my first derivative of this function is negative a omega sine omega t plus 3.5. This is important. This is not a trick. I'm saying I want you to notice that I put in this new number, this significant number, 3.5. It's not significant what the number is. It's just significant that it's a number. So I put in this number of radians. And it's there, it's getting carried along for the ride in the derivative, but it's not changing the nature of the derivative, really, because it's a constant. All that came out was the omega, not the 3.5. Again, it's not a trick. It is the point that I'm trying to make. So now I go to the second derivative, because that's what the exercise asks me to do, right? So I go to the second derivative. And I don't know why these two were called like number 3 and number 4. They should have been called number 1, number 2. I don't know, some like word processing, whatever. But now it's asking what's dx dt squared. So now it's same thing. The omega comes out again, but nothing else comes out this time. So now we have this. Right, now we just see one thing. Right, okay, so that's the answer to that. Right, so that's just the answer. Okay, so then now the next question is, okay. Okay, I don't know why the board is doing. The board will come back in a second. Please come back. Please come back. Please, well, it'll come back. I think it will. Yes. Okay. Well, it will. It will. So now this again. I'm not. Hopefully, this isn't too hard. I'm not saying it's like whoa, but I am kind of saying, wait, something is happening here. This is a set of practice exercises, but there's a little twist in this exercise. We're now trying a function we never tried before. We're not just doing blah cosine omega t. We're doing blah cosine omega t plus blah, right? And I just took 2 derivatives of it. And now I'm asking, wait, okay, I just took 2 derivatives. Does this new type of function, this more complicated, this thicker function, does this satisfy the differential equation for simple harmonic oscillation? Like, that's what I'm asking now, right? Like remember, this thing is the differential equation for simple harmonic oscillation. And here's the thing. Multiplication is commutative, right? So if I look at the second derivative answer I just got, multiplication is commutative, i.e. a omega squared is the same thing as omega squared times a, right? I mean, I can switch the order. So I can just to make this as clear as I possibly can, I can switch the order around and go like this, right? I'm just taking my answer, just taking that answer that I got there and just switching things around. But if I do that now, notice this part here is this. Like, I switch around the omega squared and the a. So now a cosine omega t plus 3.5 is what we meant by x in this case. Like, we proposed a new fancier x. a fancier x that had a 3.5 in it. And we took a couple of derivatives, and the 3.5 didn't come out. It didn't seem to affect the derivatives, but it still stayed in the parentheses. So what I'm saying is, even when we stuck in the 3.5, look, it looks like, oh my God, like, yeah, when we take two derivatives, it still works. Like, we still get back our original function times omega squared times a negative sign. So what this seems to suggest is, yes, like the answer is yes, this thing does satisfy this fancier function that I hadn't considered yesterday. This fancier function also, welcome to my bar mitzvah. Thank you, please. Yeah, please ignore that I just said that. And please excuse my dear Aunt Sally. And please note that this new fancier function, when you differentiate it twice with respect to time, you get back itself times a constant, omega squared, times a negative sign. So this function is apparently also an example of something that satisfies the relationship for simple harmonic oscillation. This thing is also an oscillator, evidently, even though it's fancier or more complicated looking than the thing we had yesterday. Let me be really clear about that, or let me try to be really clear about that. I'm saying, actually, let me go to Z's. Like, let's see, I'm going to go to Z's now. Like, what we just did was with the number 3.5 and the letter X, but there was nothing about what we just did that was specific to the number 3.5 or the letter X. Like, it was, we just noticed something about the nature of taking derivatives. So I'm going to generalize now. If in general, if we have this, okay, so now what I'm saying is, we've been saying that the solution to the harmonic oscillator is variable equals variable naught cosine omega t. It tacitly, what we've really been saying without thinking about it is omega t plus nothing. Like, we didn't add anything to omega t. What we're discovering now is you could add something to omega t and it still works. You could add any number you want to t. It could be 0, but it doesn't have to be 0, and it will still work. So from here on in, I'm going to be general about it. I'm going to say the solution to a harmonic, I'm just being mathematical for a moment. I do want to get physical in a moment. But right now I'm being mathematical and saying z equals z naught cosine omega t plus any number you like, 0 or not 0, as long as it's a number, as long as it's constant, like not a variable, as long as it's a constant, it won't mess up your derivative. And let's assume that that constant has to be measured in radians. Otherwise, it doesn't even make sense to put in the parentheses. And from now on, I'm gonna give a name to that constant. I'm gonna call it the Greek letter lowercase phi or phi. I think nobody knows. People differ over what to pronounce it. I'm gonna call it phi. Phi just like omega just stood for that other thing. I'm not assuming you already have a feeling about phi. I'm just using phi from now on to stand for the number that could go in the parentheses and could still work And therefore, I'm making a more general solution to our harmonic oscillator. Now I'm saying this is a more general way to make a prediction. Like, we don't have to restrict ourselves to the value of 0 in that parentheses anymore. The derivatives will still work out fine. That's mathematically what I'm saying. Now, physically, what does this mean? Like, who cares? What does this give us? What's the point? Good question. Okay, that lowercase letter, and I'm watching the, I know we have 9 minutes, that lowercase Greek letter phi, we use that letter to, it stands for a concept called phase constant. Okay, just like omega stands for omega angular frequency, phi stands for phase constant. Again, I know I said it on the other page, but just to be clear, like the units of phi are definitely radians. And if you think about it, what it must mean physically, it's like an extra number of radians. It's like we were going to take the cosine of just a certain number, but before we take the cosine of that number, apparently we add on this number of radians, or we subtract. I mean, depending on whether phi is a positive number or a negative number, it's saying, wait, before you take that cosine, like you picture your cosine graph, right? And you know the cosine, for example, of 0 is 1, right? So at t equals 0, the cosine graph is supposed to be at 1. So if you were looking at x equals x naught cosine omega t, right? Like at the initial moment of watching our oscillator, the oscillator is at 1 times x naught. The oscillator is at its amplitude, its initial and maximum position, right at t equals 0, right? If you just have normal, I should write, yeah, all right. Oh, yeah. Just an example. All right, just in quick example. So what does that thing do? What that phi, that phase constant, is it's a head start or a delay in phase with respect to phase, and by phase we mean cycle essentially. So just as by putting it in the parentheses, it just affects where the oscillator is in its cycling when you start your stopwatch. If you don't have a phase constant at all, if the phase constant is 0, it assumes that we started our stopwatch at the moment that the oscillator was actually at what we would generally call the beginning of the cycle, the amplitude position, the initial position, the farthest outstretched place from equilibrium, right? But if there is a phase constant measured in radians, if there's a phase constant such as, for example, here, pi/2 radians, it means the oscillator is, everything else about the oscillator is the same, but it happens to have not been at an amplitude position when we started our stopwatch. It either has a delay or a head start, depending, I mean, everything is circular, so depending on how you think about it, it's either a delay or a head start by some portion of the cycle. So in this case, if I just took an arbitrary oscillator whose angular frequency happened to be pi, like an oscillator is just doing pi radians per second, that means a half a cycle per second, right? Just arbitrary example. And it was an amplitude of 5, arbitrary example, just so I could have numbers to plug in and see, right? I'm just comparing, if we just do an oscillator with no phase constant, then at t equals 0, the thing is at the amplitude position. Just plug in, 0 for t, times pi is 0, cosine of 0 is 1, 1 times 5 is 5, right? That's just a unphased oscillator, so to speak. But if we put in a phase constant of pi/2, that means the oscillator is a quarter of a cycle ahead or behind our timing, right? A quarter of a cycle. Why? Because there's 2 pi radians per cycle. So pi radians would be a half a cycle. Pi/2 is a quarter of a cycle. Again, I'm just picking it as an example because I think it's kind of a clear example, but it's just an example. But so there, if I just put that in and you just plug in the numbers, if you plug in 0 for t, then 0 times pi is still 0, but 0 plus pi/2 is pi/2. So we take the cosine of pi/2, and the cosine of pi/2 radians is 0. So that oscillator would already be at the equilibrium position, or wouldn't have gotten to the amplitude position once we started timing. So phase constant means a head start or a delay in the cycle. It's actually not, we don't really care. If we only have one oscillator, there's no really even point in, well, yeah, I'll write this now because I know class is about to end, but okay, that's as far as we're going to get today. I see it's 129. But so the phase constant is a head start or a delay. Like always in physics, the concept of marking a head start or delay is not really that meaningful or necessary if you only have one oscillator. Like if you have one oscillator, why not just start your stopwatch whenever it's convenient for you, like when the thing is outstretched? That's what we do. When we only have one oscillator, we generally don't have a phase constant, which is why we spent 2 weeks not worrying about this. But if you ever have more than one oscillator and they're starting at different points in their phase, you can start your stopwatch when one of them is all the way out here. But if they're not doing the same thing, then you can't do that for all of them. So this becomes a particularly relevant quantity to track when you're comparing one oscillator to another, which is exactly what we have to do next week when we start putting these oscillators together and building wave pulses, which is actually the point of all of this. is to build a wave pulse out of a bunch of oscillators. In order to do that, we need a bunch of oscillators who are out of phase with one another. So that's it. You've been very, very patient. Thank you so much. You can go. I'm going to just hang out in case there's questions or anything. Blah. I'll upload all this. Blah blah blah. But blah 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 and blah blah blah. And you've been very patient. And thank you. And have a great weekend. And I will post more homework soon, since you all are pretty much caught up, which is great. And I'm caught up with you, which is greater. But thank you. And I will stop. But I will answer questions if there are any. Goodbye. Have a great weekend. Yes, thank you. You too. Thank you. Yes, you too. Thank you. Thank you. You too. Okay.
Bye, Professor.
Thank you so much. Have a great weekend, Ashley. Okay. 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 And Luna, you good? Or hello, Luna. It's a full Luna. No, it's a waxing gibbous Luna. Luna, you. Okay, but thank you, and thank you everybody who's anybody, John Jay or not. I'm totally touched and moved and surprised. And going once, going twice, going thrice.